In this video, we're going to discuss simultaneity and the relativity of simultaneity. This is the most important concept to grasp in order to understand special relativity. Why? Well, to build a theory of space-time, we need to start with a precise definition of time. Einstein showed that we can understand points in time through simultaneous events, and he assumed that simultaneous events must be defined using light rays. So the speed of light, the fundamental constant that plays a most fundamental role in special relativity, enters the theory through this phenomenon. So first we are going to define what simultaneity is, then we're going to see through thought experiments, as Einstein did, how any agreement on what is simultaneous gets lost between inertial reference frames. Then we're going to basically derive the rest of special relativity using this idea. So let's start with a thought experiment. Imagine a group of three friends, Alice, Bob, and Charlie, obviously, so we can call them A, B, C. Alice and Charlie have watches, and they want to test whether their watches are synchronized. They come up with a rather impractical way to do it. So they agree to stand a distance L apart from each other, such that Bob is in the middle, and then Alice and Charlie take their flashlights and agree that they're going to turn on their flashlights when their watches hit 12 noon towards Bob. Now Bob has to have just inhumane reaction time here, but he's going to test whether both of those beams arrive at him at the exact same time. If this is the case, we are guaranteed that Alice and Charlie have perfectly synchronized watches. So what has happened simultaneously in this setup? Well, first, Alice turns on her flashlight such that the flash is simultaneous with her watch hitting 12 noon, according to her time. Charlie does the same thing on the other side with respect to Charlie time. And then Bob, in the middle of the two, tests whether Alice and Charlie time are synchronized. And if this is the case, Alice and Charlie turning on their flashlights was a simultaneous event. Now, so far this is rather obvious, right? It seems like it's overkill to detail something so simple. But trust me, relativity gets very confusing very quickly, and people fail to understand it because they don't take their time through the foundations. We're going to set them as hard as stone, and they will carry us through the difficulties. To do this, we need to be very precise by what we mean by everything, even if we think that we already know what it means. So, of course, this is how simultaneity works. It's intuitive. But the point is, it's not just how it works. This is what simultaneity is. So Einstein insisted that this is the very definition of a common time between two or more observers. So simultaneity, in a way, is what connects time through space. And this connection fundamentally happens at the speed of light. So by using an experiment like this with light rays, it's like we're tapping into how this connection is really happening. Now, so far, we have to point out this is an assumption that Einstein's made to define things this way with light rays. But it's an assumption that makes many predictions which can be tested and confirmed. And of course, that is what has been happening for almost 120 years now. So we are in good hands. Now, to see the importance and consequences of this definition, let's further the thought experiment. So the first thing we're going to do is we are going to get a moving train. This is a train. It's moving towards the right at a constant velocity v. That means that it is an inertial reference frame. We're going to put our group on the train and have them repeat the experiment here. What would change? Well, the principle of relativity, the classical one put forth by Galileo, it says that there's absolutely nothing that will change. There are no preferred inertial reference frames for the laws of physics. So all experiments yield the same results on the train as they did on the ground, which was also an inertial reference frame. So whether you throw a tennis ball or build a particle accelerator on the train, you will always get the same results. This also means that there is absolutely nothing you can do to even tell that the train is moving, without looking outside the window, of course, and seeing that the rest of the world is moving backwards. So that is by referring to another inertial reference frame. This is because velocities are just fundamentally relative as a concept. So keeping that firmly in mind, the interesting things start to happen when we let inertial reference frames interact. So we can add a fourth observer, call her Denise, who will watch the experiment happening on the train from the ground. To understand her perspective, we need another ingredient here. It's provided by Maxwell and added in by Einstein, the laws of electrodynamics. Namely, they're insisting that the speed of light be a constant and the same constant no matter what. So you would have seen these epsilon and mu constants in the laws of electrostatics like Coulomb's law and the Biot-Savart law. These are fundamental constants of space that quantify the strength of electric and magnetic fields, how they penetrate space, if you will. So if you write down the Maxwell equations just for a vacuum, they will still be there. If you write all four of the Maxwell equations together, you get to these second-order forms, and these equations obey a wave equation in 3 dimensions. That is what describes an electromagnetic wave. This is light. So the wave equation then requires for the propagation speed of the wave, so light, to be 1 over the square root of these 2 constants. Again, they are fundamental constants of space. They are laws of physics, so they're not going to change because you're on a train. Now, this equation in yellow says that it is a law of physics that the speed of light be exactly this constant. And so the speed of light has to remain invariant through inertial reference frames. So even though the train is moving forward with velocity v, when the flashlights are turned on, Denise won't measure the light beams moving with velocity c plus v or c minus v. So, with that, we now have the 2 postulates in place. These are the postulates that Einstein used to build relativity. The classical principle of relativity, as we have invoked already, and the constancy of the speed of light. Equipped with these, we can now analyze Denise's point of view, and we will draw the conclusion that simultaneity is relative. As we've agreed already, Bob receives the pulses simultaneously as before. However, in Denise's perspective, Alice's light pulse moves in the same direction as the train is, while Charlie's moves in the opposite direction, while Bob is moving along with the train. So Denise measures that Bob has different relative velocities to both of these light beams. He moves towards Charlie's pulse, so that's c plus v, and away from Alice's, so that's c minus v. Now we just said that the beams don't move at c plus v or c minus v. So I want to clarify what we mean here. The beams are moving at c, as measured by Denise. But Bob is moving relative to these beams because he is on the train. Remember that Bob still measures both beams to be moving at c. So it is correct to add the velocities this way, since both of the velocities are measured by Denise from another frame. So these light pulses will take different amounts of time to arrive at Bob, all as seen by Denise. We can calculate by how much, so call TAB the time it takes for Alice's beam to arrive at Bob. That is going to be L divided by the relative velocity here, which is c minus v. For Charlie to Bob, the velocity is larger, so TCB is going to be L divided by c plus v. So it takes longer for Alice's beam to get to Bob than Charlie's does. So let's carefully make our conclusions here. Even though Denise measures that it would take different amounts of time for the beams to reach Bob, she still has to see both of them reach him at the same time. That is physically what happens. They have to agree on that. For example, imagine that Bob gets shot from both sides with laser pistols. He gets hit by both of the laser beams at the same time. The details of Bob's sudden violent death need to be agreed upon by all frames. No one can argue that one of the shots got to him before the other because the forensics will show the same result. But it's also true that the time it takes for the light pulses to arrive at Bob are different. So there is only one conclusion left. The pulses were not emitted simultaneously, according to Denise. So what Denise sees is that Alice first emits her flash and then Charlie emits it a little later. They're not simultaneous because they take different amounts of time to reach Bob, but they have to reach him at the same time. Denise doesn't receive the flashes at the same time either. She just concludes that Alice and Charlie didn't have synchronized watches. In other words, simultaneity, just like velocity, is a fundamentally relative concept. So, if this seems confusing now, don't worry, it is. We will develop more tools to get better intuition about all of it, the most important being space-time diagrams. That'll be the next video. But for now, let's play around with this idea a little more to understand it and its implications a little better. So, to warm up, I'll ask you a question. We know that from Bob's perspective, Alice and Charlie still have synchronized watches. From Denise's perspective, whose watch is ahead? Is it Alice's? Is it Charlie's? So thinking about the question from Denise's perspective can get confusing. We said that Alice's beam happens earlier than Charlie's does, so that they reach Bob at the same time, right? Does that mean that Alice's watch is ahead? Yes, it does, because if it's ahead, then her watch hits 12 noon earlier than Charlie's does. So she emits her beam earlier. Well, just to be sure, it's easier to think of it in Bob's perspective. So go all the way back to the beginning of the video where they did the experiment on the ground. Over there, if Bob received Alice's pulse earlier than Charlie's, it would mean that Alice's watch hit 12 noon earlier than Charlie's did. So her clock would be ahead. Now this of course applies to just anywhere on the train. The rear clock, the clock that is located at the rear of the train, is always going to be ahead of the one that is located at the front. So if we were to just imagine a bunch of clocks on the train, let's put one here, 2, 3, let's put 4 clocks on the train. So say if the first one looks like this, the second one would look like this, the third one a little more behind, and the fourth one a little more. Now I should point out that this has nothing to do with time dilation so far. All of these clocks tick at the same rate relative to each other. That will also be the case with time dilation, of course. They just have a delay in between each of them, and that delay depends on the distance between them, which we will now show. So that brings us to our second question. And I should warn you, it is a little trickier than it looks. By how much is the rear clock ahead? Well, at first the answer seems obvious, right? We have already calculated that TAB is L over C minus V and TBC is L over C plus V. So if we go ahead and take a difference, TAB minus TBC is going to be equal to 2LV over C squared minus V squared. It is totally fair to answer with this. The problem is there are Lorentz transformations to consider, and this answer would be wrong by a factor of gamma squared. So in this delay, time dilation and length contraction have an effect. And in the following videos, with our space-time diagrams and our Lorentz transformations, we're going to see exactly how this works. But for now, there is still a way to kind of get around all that, to bypass the Lorentz transformations and still get the right answer. To do that, we need to answer this question. Where can we place Bob between Alice and Charlie so that if Alice and Charlie emit their flashes simultaneously with respect to Denise this time, Bob would also receive them at the same time? So we're no longer going to put Bob in the middle of Alice and Charlie, but find another spot so that this is what happens. So let's redraw our shape to unpack exactly what this means. So previously we had Bob in the middle of Alice and Charlie so that he's a distance L to both of them. We know that Denise measures that Alice's beam takes longer to get to Bob than Charlie's does. So if the beams are going to be simultaneous to Denise, we need for Bob to be closer to Alice so that he can receive them at the same time. So how can Alice and Charlie emit their beams simultaneously with respect to Denise? Well, again, Denise sees Alice emit her beam first and Charlie's beam later. So for her to see both of the beams simultaneous, what they need to do on the train frame is to have Alice emit her beam later than Charlie's. So they may agree, for example, that Charlie will wait for his watch to hit 12 noon and Alice will wait 12 noon plus 1 second, if we exaggerate the effect here. So that on the ground, Denise sees the beams are simultaneous. Anyway, let's do the math now. So what we are trying to do is get the two time periods that we have found earlier, TAB and TBC, to now be equal. The velocities are the same, so we are doing that by changing the distances. They were previously just L and L. Now we can call them LAB and LBC. So this yields the equation that we need to solve. But the problem is we have two unknowns here. Both of the distances are unknown. Luckily, we also have a constraint. Since the distance between Alice and Charlie is still 2L, we need LAB plus LBC to be equal to 2L. So we just need to solve one of these equations and write it into the other one to get these distances. Here we'll just do algebra, and I know that it sucks to watch someone else do algebra, so I'd recommend you solve this yourself anyway to fully grasp it. I'll just take a sip of coffee and fast forward through my solution. Okay, so now we know where Bob needs to stand to get the beams at the same time. So he is L C minus V over C away from Alice, and L C plus V over C away from Charlie. Now to be clear, this means that Denise will conclude that the beams are simultaneous, but Bob can't make that conclusion. He ruins the symmetry of the experiment by not standing in the middle. He receives the pulses at the same time because he's further away from the one that gets emitted earlier. So the effect isn't just undone. They cannot agree on what is simultaneous. That is impossible. It is relative. So all we're doing is we're kind of playing around to get the equations, to get them to agree that they get the beams at the same time, not agree on simultaneity, and this allows us to bypass the Lorentz transformations. If you're familiar with them, it would be a great exercise to pause and ponder on how it actually happens. Now, what was the question again? Oh, we're trying to find the delay between their clocks. Well, now we have a system where kind of everybody agrees on when the beams get to who, so we can now test the delay on the train. This is important. So we can use these distances and divide by the velocities to find how much time the light beams take to get to Bob. Now, if we use Denise's velocities, notice that we would just be dividing by c minus v and c plus v, and we would be left with L over c on both sides. And that's what we expect, because now the beams are simultaneous to Denise. The delay is now on the train because Alice agreed to send her pulse later than Charlie did. We're trying to find by how much they have to do that. So we have to divide both of these distances by c. So we can call these time periods as measured on the train TAB prime and TBC prime. So we have L c minus v over c squared and L c plus v over c squared. Now we just need to take their difference. Let's start with the larger time period, which is TBC prime minus TAB prime, and we can just open these parentheses to make it simple. So we have LC plus LV minus LC plus LV, all over c squared. So from this, we get that the answer is 2LV over c squared. This is an important formula because now the rear clock in the frame that is moving relative to the observer is always ahead, given by this formula. So, as I've mentioned, notice that it depends on the distance between the clocks. Alice and Charlie are separated by 2L, and that's what we have in the equation. So, the fact that the rear clock is ahead in the other frame is usually what is forgotten when people run into paradoxes and get confused. So this will prove very useful when we are solving problems later. Okay, so if all of this seems confusing now, as I've said, don't worry, it is. On the next video, we will equip ourselves with space-time diagrams and Lorentz transformations, and everything will fall into place. So, thanks for watching, and I'll see you there. Before I end this video, I wanted to note that Einstein, in his 1905 paper, makes his definition of simultaneity using mirrors. So it works the same way, but this way we just need Alice and Bob. So let's say that Bob has a mirror, Alice sends a light pulse towards Bob, and it gets reflected back to Alice after time TAB. If the time it takes for the ray to get to Bob is equal to the time that it takes for it to get back to Alice, Alice and Bob have synchronized watches. Well, you can show that this is equivalent to having 3 observers because that's how mirrors work. I just find it easier to grasp the concept with 3 observers because the experiment is more obvious. You just need Bob to check whether the 2 beams get to him at the same time. Whereas if you use mirrors, you somehow need to keep track of how long the light actually propagates to cover that distance. So it seems just more difficult to find a way to measure that amount of time passed, whereas it's easy for Bob to just check whether the beams were simultaneous. Either way, it works exactly the same way.